In this video, I'm going to prove the power. We're going to prove the power rule. The power rule states that if f of x equals x to the n, then f prime of x is equal to nx to the exponent n minus 1. So an example of that would be if f of x equals x to the 5, then f prime of x will be 5x to the exponent 4. Okay, well, how do we prove such a thing? Well, we begin by using the definition of derivative. We know that the limit as h goes to 0 of f of x plus h minus f of x all over h will be the derivative. And we know that in this example, f of x is equal to x to the n, which means f of x plus h is x plus h quantity to the n. So we can sub in x plus h quantity to the n for f of x plus h, and we can sub in x to the n for f of x. And that's what we do in the next line. Now, recall difference of nth powers factoring, and let's use as our example to help us recall it. Let's use a to the 5 minus b to the 5. We know that a to the 5 minus b to the 5 has a factor in front of a minus b. And then we can also write, in this case, we'll think of n as being 5. We're doing difference of nth powers. Here we're doing difference of fifth powers. So for this example, n is 5. In the second bracket, we're going to have a to the n minus 1 times b to the 0. So we'll leave that out. Plus a to the n minus 2 b to the 1 plus a to the n minus 3 b to the 2 plus a to the n minus 4 b to the exponent 3. And then finally, we get to the end. We have a to the 0, and we have b to the exponent n minus 1. Well, if we generalize that to n terms, we see that we've got, just like we had starting our first one, starting this, just like we had in the example we just did where we did difference of nth power, difference of fifth powers factoring, we start with a to the n minus 1. And then the next term is a to the n minus 2 times b. And the next term is a to the n minus 3 times b squared. And then we keep on going. Our third last term will be a to the 2 and then b to the n minus 3. Remember, in this case, n was 5, so n minus 3 would be 2. A to the 2, b to the n minus 3, just like we have there. And then ab to the n minus 2, which is, in the case of fifth power, is ab cubed. And then finally b to the n minus 1, again, in the case of fifth power, is b to the 4. So we see that if we generalize our knowledge of each individual difference of nth powers to the general difference of nth powers, we see that our second factor equals the second factor that we've written there. Now, in our case, that's what a to the n minus b to the n is. A to the n minus b to the n is this long thing we've written here. Well, in our case, we are a to the n minus b to the n. Our a is x plus h, and our b is x. If you look here, that's what a and b are. A to the n minus b to the n, a is x plus h, b is x. So what we're going to do right now, we're going to sub in for all the times that we see a, we're going to sub in x plus h. And for all the times that we see b, we're going to sub in x. Okay? So we do that in the next line. And we see we've got a to the n minus 1 plus a to the n minus 2b plus a to the n minus 3b squared, etc., all the way to the end, just like we had in our last line. Now, x plus h in brackets minus x is obviously the same as x plus h minus x. X plus h minus x, this circled factor here, simplifies obviously to a factor of h. So in this last numerator, you'll see that we have two factors, h, and then the very long factor as well. In the denominator, we only have one factor, h. So we can cross out these h's, and we'll be left with the limit as h goes to 0 of that second, the really long factor in the numerator. And this is something that we can sub an h value of 0 in safely. And that's what we're going to do ultimately. So after crossing out those h's, like we said, we're going to plug in our h value of 0. We're going to plug in our h value of 0 for all those h's. And that's what you see in the second last line. Well, that's what you see in the second last line here. And then what we can say is x plus 0 to the n minus 1 is the same as x to the n minus 1. X plus 0 to the n minus 2 is the same as x to the exponent n minus 2. X is the same as x to the 1. If I'm going to multiply these two together, I realize that I have powers with like bases, so I just add those exponents. So I take n minus 2 plus 1, and I add them, and I get n minus 1. And ultimately, that's what that term is going to end up being. Okay, x plus 0 to the n minus 2 times x becomes x to the n minus 2 times x, which will become an x to the n minus 1. Now here, after subbing in an h value of 0, I get x plus 0 to the n minus 3 times x to the 2. Obviously, x plus 0 to the n minus 3 just becomes x to the n minus 3. And then again, we're multiplying by x to the 2. If I'm going to multiply these two powers together, they have like bases. And so I'm going to add those exponents together. N minus 3 plus 2, that's equal to n minus 1. So I get another term of x to the n minus 1. Similarly, here, this next term there, that'll be, we've got powers with like bases, so I can add the exponents together. I get 2 plus n minus 3, which ultimately equals n minus 1. And what you see there is all of these, after subbing in an h value of 0, all of the terms in that second bracket, the really long one in the difference of nth powers factoring, all of those end up just being x to the n minus 1. So we're just adding a bunch of equal terms after subbing in that h value of 0. Well, it'd be nice to know how many of those terms there are. Okay, so that's what we end up getting. Well, how many terms are there? Well, let's go back to our original difference of nth powers factoring. In our original difference of nth powers factoring, we went through various examples. In the first example, we were doing difference of second powers factoring, and our second factor had 2 terms. When we did difference of third powers factoring, our second factor had 3 terms. When we did difference of fourth powers factoring, our second factor had 4 terms. Well, it stands to reason that when we're doing difference of nth powers factoring, our second factor is going to have n terms. Well, going back one slide, that's all that we have here. That this long factor here, all of those are just the terms from the second factor of the difference of nth powers factoring after subbing in an h value of 0. So in other words, we have n of those terms. Okay, so like it says on the right-hand side of this slide, in each case, the first bracket is a minus b, and this was simplified to h and crossed out in the denominator. Then the second bracket always contains n terms. Now, each one of those terms in our expansion, is equal to x to the n minus 1. Since we have n of them, we have n x to the n minus 1. And that is the expression for the derivative. And we've just proven the power rule. If f of x equals x to the n, then f prime of x equals nx to the n minus 1. And that's going to save us much time in this course from having to always go back and do the first principles method using the definition of a derivative.